The following definition is not strictly needed in the sequel, but nevertheless, it's good to know and it'll prove useful in more advanced courses. Definition, let f from ab to r be a bounded function. Actually, on second thought, I don't need it to be defined on an open interval ab. It could be any set S. Let f from S to R be a bounded function. We define the norm of f to be norm f written with 2 bars like this is by definition equal to supremum of x in S f of x. Okay, so all you do is you look at all the values of f of x and take the supremum. Such a supremum will exist simply because this is a bounded function. Now, in this course, the use of this will be we will make only rudimentary use of this, and that is contained in the following proposition. Let Fn from S to R be a sequence of bounded functions. Then Fn converges uniformly on S if and only if for each epsilon greater than 0 we can find capital N in N satisfying norm Fn minus Fm is less than epsilon when n comma m is greater than capital N. Okay, so this is sort of the Cauchy criterion. This is the Cauchy criterion for uniform convergence. Okay, now I'm not even going to prove this Cauchy criterion. It is basically unwinding the definitions. At this stage of the course, such a proof should be straightforward to you. When you see the statement, you should be able to see a proof of such a statement. So I leave it to you to fill in the gaps and write the proof of this proposition. Now let me make some more advanced remarks regarding this so-called norm of the function. Now this will not make sense to you if you are not familiar with the theory of vector spaces. However, it might still be useful for you to just lend your ear for a few minutes. Now, if you consider functions from S to R, it's clear that you can add two functions, you can multiply two functions, you can multiply a scalar and a function. So essentially, if f comma g, so let me highlight this as a remark. If f comma g from S to R are bounded functions, then so are f plus g, fg and cf for all c in R. These are all going to be bounded functions. Moreover, these operations satisfy several algebraic properties. For instance, if you take f plus g, it's same as g plus f. If you take f into g plus h, where h is a third function from S to R that is bounded, this is nothing but fg plus fh. Okay, in short, if you let Bs to be the set of bounded functions, on R, then not bounded functions on R, bounded functions on S, bounded functions on S, then BS will be a vector space and a ring. In short, it will be an algebra. It will be an R algebra. Now, if you don't know what vector space, ring and R algebra are, nothing to worry about. These are just straightforward generalizations of various objects that you're already familiar with, namely the integers and the common vector spaces Rn. Okay, these are just natural abstractions from the familiar objects that you have been studying way back from maybe second standard or third standard. You have been possibly exposed to integers way back in third standard. Okay, so this collection of functions which are bounded on a given set S form an algebra. Not only that, we can define distance, which I'll put in quotes, distance in this algebra using this norm. Now this norm you should think of, as the notation suggests, in terms of the absolute value or modulus function that you have been using throughout this course. The absolute value function on the real number satisfy a number of simple properties, the most important of which is the triangle inequality. You can actually check that this norm satisfies similar properties. Okay, in short, this BS with this norm becomes a normed vector space, and one can do analysis on this vector space. Okay, now if you have the good fortune of taking a functional analysis course in the future, you will study this space BS in more detail. You can also study some topological aspects of this. Once you define a distance using the general theory of metric spaces, you can define what an open set, closed set, compact set, so on and so forth are in this space BS, and you can study many theorems. For instance, what are the subsets of BS that are compact? That's an interesting question to ask. So this is all at a more advanced level, so I will not be dealing with that now. Essentially, all I need is just this notation for the norm of a function and this Cauchy criterion for uniform convergence, whose proof is utterly straightforward. Okay, so enough preliminary remarks. Let's come to the main topic of this module. That is the behavior of uniform convergence with respect to differentiation and integration. So without belaboring the point, let me just state the theorem, or at least the first theorem. Let Fn be a sequence of continuous functions on the closed interval AB. Okay, suppose Fn converges to F uniformly. Then of course F is continuous, which we have already established in an earlier module. But the key thing is, and integral a to b Fn, which exists because Fn's are all continuous, limit n going to infinity is equal to integral a to b f. So essentially what is happening is this limit can be pushed inside. So essentially the behavior of uniform convergence under integration is the best possible behavior. You cannot get better behavior than this. Proof. Well, let's start with the quantity that we are interested in, integral a to b fn minus integral a to b f. This is the quantity that we are interested in. Well, by linearity, this is going to be integral a to b fn minus f. Okay, this is just by linearity, and this is going to be less than or equal to b minus a into supremum, or let me invoke the notation that we have already concocted precisely for this purpose, norm fn minus f. Okay, this is just basic property of integral. This is just the basic property of Riemann integral. Okay, so tacitly I am using the fact that this is going to be less than integral a to b mod fn minus f. I am using that. After that, I get this in an easy way. Okay, how does this help? Well, norm fn minus f can be made less than epsilon for suitably large n. Suitably large n. Okay, which just means mod a to b fn minus a to b f can be made arbitrarily small. For large n. That's it. The proof is done. It's an utterly straightforward theorem, and it shows that integrals behave very, very nicely with respect to uniform convergence. Okay, now onwards to differentiation. Here things get a bit tricky. So before I even state the theorem, it might be a good idea to expose a flaw in our line of thinking, because if you have been following this theorem, your immediate reaction should be, if fn converges to f uniformly and fn's are all going to be differentiable, then f is differentiable, and furthermore f is going to be the derivative of f is going to be nothing but the limit of derivatives of fn. That's what you would think is going to happen, but not so. So let's see example. Let's consider sine n squared x by n squared. Okay, let me just take it from, for convenience, close 0 1 to r. Let's take it here. Okay, now because sine of anything, sine of y is modulus is less than or equal to 1, it is trivial to show that sine n squared x by n squared converges uniformly to the 0 function, to the constant function 0. Okay, so this is fn, of course. So I leave it to you. This is a very, very easy to show thing. Okay, now where's the catch? Well, what is the derivative of fn? Well, fn prime is just cos n squared x, and the n squared in the denominator will vanish by chain rule. Well, look at fn prime. And look at f prime. F prime is, of course, identically 0, because the sequence fn converges to the identically 0 function. Look at fn prime and consider fn prime of 0. Okay, consider fn prime of 0. But we all know that cos 0 is 1. So fn prime of 0 does not converge to f prime at 0. It does not converge to f prime at 0. So the upshot is that it is not true. That if fn converges to f uniformly, then, and if both fn and f are differentiable, then fn prime converges to f prime. This is simply not true. What you naturally expect is not true. So I have to state the next theorem, which is going to tell you when this happens in a much more nuanced way. So theorem. Oh, by the way, it needn't be the case that the limit function f is differentiable. It need not be differentiable at all. In the exercises, you will be asked to show that a particular sequence of functions converge to the modulus function, the absolute value function, which we all know is not differentiable at the origin. So uniform convergence does not even guarantee that the derivative of the limit function exists, even if the derivatives of all the fn's exist. There's no guarantee. So the next theorem is the behavior of uniform convergence under differentiation. Let fn be a sequence of differentiable functions on closed interval a b, and here I'm going to require a greater than b for obvious reasons. Okay, not a greater than b, a less than b. Okay, now the hypothesis that I'm about to write is really weird. Assume number one, not that fn's converge uniformly to f. Assume that fn prime converges uniformly to a function f. Okay, so the hypothesis is that the sequence of functions, the sequence of derivatives converge uniformly to a function f. Okay, so I must add one hypothesis: continuously differentiable. That means the derivatives are all continuous functions. This is the first hypothesis. The second hypothesis is assume that for some x naught in the closed interval a b, we have that the sequence fn of x naught converges. Okay, so these are the two hypotheses. The first is that the derivative functions fn prime converges uniformly to a function f. This function f from a b to r will necessarily have to be a continuous function, simply because we are assuming that fn primes are all continuous functions. And the second assumption is that for some x naught in the closed interval a b, we have that the sequence fn x naught converges. Okay, so for one point in the interval, closed interval a b, the sequence fn x naught converges. Okay, then the conclusion, the grand conclusion is that then fn converges uniformly to a function so if you don't mind, let me just change this to g. This is not such a big deal, but I like to be a bit of nice when it comes to notation. Then fn converges uniformly to a function f from a b to r such that f prime is nothing but g. Okay, so under the hypothesis 1 and 2, the sequence fn itself converges uniformly to a function f from a b to r, and not only that, the derivative of this function is the limit of the derivatives of fn. Okay, proof. So how should we approach proving this theorem? We already know that uniform convergence behaves very nicely with respect to integrals. So what we are going to try to do is to somehow apply the previous theorem about uniform convergence and integrals. But the hypothesis we have here is the uniform convergence of the derivatives. So naturally, the only way to start this proof is via the fundamental theorem of calculus. So what we do is we write this function fnx as integral a to x fn prime plus fn of a. Okay, this is just the fundamental theorem of calculus. This is just the fundamental theorem of calculus. We can just write this. Now, how does this help? Well, we know that fn x naught converges. We know that fn x naught converges, and we also know that integral a to x fn prime converges. Note x is fixed. So write fn of x equal to integral a to x fn prime. This is true for all x in AB. Okay. So for a fixed x, we know that fn x naught converges. We also know that we have to change this. We also know that integral a to x naught fn prime converges. This is the previous theorem. Right? The behavior of uniform convergence under integration. Because of this, fna converges to some number, let's say c. Because fnx converges and because fnx not converges, that's just hypothesis 2, and because integral a to x fn prime integral a to x not fn prime converges, that's just hypothesis 2 plus the previous theorem, we must have that fna converges to some c in R. Okay. So what we do is the following. We now consider this equation star. We now consider star. Again, we have that integral a to x fn prime converges. And of course, we have just shown that fna converges. So, fnx converges pointwise. Or rather, to be a bit more modern, this is perfectly correct mathematical notation if you are a bit old school. So fn converges pointwise to a function say f. So note the key idea. We have this equation star, but just from star you cannot conclude that fnx converges because we don't know the behavior of fna. But from the fact that fnx not converges, we were able to show that fna converges. Once we have that, we know that fn converges pointwise to a function, say f. Okay. Now, all we have to do is show that this convergence is uniform. Right? Well, to do that, what we do is we consider integral a to x fn prime minus integral a to x g. Okay. Recall g was the sequence of g was the function that the sequence of derivatives converge to. Okay. Now, what we are going to do is the following. We are going to write this as modulus integral a to x fn prime minus g. This is just linearity of the integral, and this is less than or equal to, by a basic, again the same argument that we have used before, this is just b minus a norm of fn prime minus g. Okay. So what does this tell us? Well, this tells us that norm fn minus f, which is actually nothing but supremum of mod fn x minus f of x as x ranges through the closed interval ab. So let's analyze mod fn x minus f of x. Well, fn x is already going to be just integral a to x fn prime plus fn a, and because f is just the limit of this expression on the right hand side here, f is nothing but integral a to x g minus c. Recall, c was the limit of fn a. Okay, so we have less than or equal to this. Fine, but this is less than or equal to, by triangle inequality, integral a to x fn prime minus a to x g plus mod fn a minus c. Okay, and we just saw now that the first term, integral a to x fn prime minus integral a to x g, this is less than or equal to b minus a times norm fn prime minus g. This can be made less than epsilon by 2 when n is large. Similarly, this quantity can be made less than epsilon by 2 when n is large. Net upshot is that fn converges uniformly to f. Okay, and the fact that f prime is equal to g is just the fundamental theorem of calculus. Okay, so this concludes the proof. So the behavior of uniform convergence under differentiation is still nice, but not as nice as one would expect. Usually what will happen is this fact that this fn converges at one point, that's just for silly reasons that we are writing that hypothesis that fn x naught converges to some constant something converges at one point. That's just for writing the result in the great generality. We are writing that. Usually in the scenario that you are in, you will usually have an easy way of showing that fn's converge throughout the region AB. You will not be having it will be very unusual that you will have convergence at only one point. Okay, so this concludes this module. This is a course on real analysis, and you have just watched the module on behavior of uniform convergence under integration and differentiation.